All right. Well, thank you everyone for joining. We're very happy to have some esteemed guests here today to speak about downwash and outwash. Just a little bit of background about the Vertical Flight Society for anybody who doesn't know. So we are the International Professional Society for those working on vertical flight and as well as advanced air mobility in general. So we don't require that you do a vertical takeoff and landing, but it's in that general domain of using power for lift. So again, we're an educational society. Those in the UK would call us a learned society. And we're all about advancing safety and acceptability and education. And that's really what this talk today is about, is educating ourselves on downwash and outwash and to help try to make safer aircraft. We are a membership society, so anybody in the world can join us. We've got VTOL.org as our website. And we've been doing a lot of stuff in infrastructure over the last really 6 or 8 years. We started a series of infrastructure workshops. It was supposed to be on March 17th, I think it was, or March 19th of 2020, but it was canceled because of COVID. So we learned how to do online webinars. We've also had live webinars since in the last couple of years, live workshops, in-person workshops. And it's really been an opportunity to bring industry, government, regulators and others together to understand the challenges of advanced air mobility infrastructure. And now with the incorporation of advanced air mobility in the US, we've got the vertiport engineering brief that's now being incorporated into the heliport design guideline. It's going to be renamed the vertical lift infrastructure design guideline. There'll be heliports and vertiports and STOL ports, but all under this vertical lift infrastructure umbrella. You can find out more at vtol.org/infrastructure. That's where we'll have the home for our downwash page. We've got a lot of resources, a lot of reports about infrastructure, about downwash and outwash that we're going to put here. And we have our 81st annual forum in a few weeks in Virginia Beach. So those who are in the area or who are planning to attend or who would like to attend, it's going to be a great event with about 1,100 attendees, 300 some technical presentations, and dozens of less technical presentations. But we have a workshop planned for the Monday before it kicks off, Monday, May 19th. We're really looking to bring together people in industry, academia, and government agencies to look at this challenging issue. This has been brought to the forefront, I guess, in the media and whatnot because of a fatal accident that happened in the UK that you'll hear about. In the US, particularly, there's not really a reporting system for people who are injured by helicopter or vertical flight, outwash and downwash. It's generally settled out of court. So we have kind of a problem where we don't know the extent of the problem. We don't have a lot of data on helicopter or eVTOL downwash and outwash. And generally, to date, our models have shown to be not very good. Luckily, with the work that Dr. Mike Pryce has sponsored here at the UK CAA, which you'll hear about, some of those issues are being resolved. Also, the FAA through Wolpert and Continued Dynamics, Advanced Rotorcraft Technology have done some work in this area, and this area is increasing. So the helicopter manufacturers and the eVTOL OEMs are now helping to provide more data, and we hope that some of these issues will be resolved. With that, I'm going to, let's see, did Rex show up?
Rex here? I am here, sir.
Thank you much. Okay, Rex, over to you.
Thanks, Mike. As Mike said, downwash and outwash is a thing. It's always been a thing. As aircraft have gotten heavier and disk loading has increased, we've seen that thing manifest into more damage and also personal injury. In the US, we have had personal injury. With that, we've seen litigation take place. And so in some cases, that litigation has ranged upwards of $2 to $3 million at the end of the day. So in the prevention of that, understanding what downwash and outwash is for helicopters is huge. We've seen what the UK has been working on. We've seen what the Australian government has been working on. And now here in the United States, we're also, banding together with everyone. And with that, I'd like to introduce our two speakers today. I've had great conversations with both. Richard Brown from the UK is with Sophrodyne. He is PhD working for his own company, works closely with the UK in doing the research, both in the private sector as well as with academia. And then Mike Pryce, working for the Civil Aviation Authority in the UK, working specifically in emergency policy specialist, developing flight operations for this next generation of aviation. So with that, I'm going to go ahead and turn it over to you, gentlemen, and I'm not sure who's going first. Who's
We
going
are.
first?
I am.
All right, Mike, it's all yours.
Okay. Thank you, Rex. Thank you, Mike Hirschberg. And thank you, everybody, for joining us. I'd say good morning, good afternoon, good evening, depending on where you are. I'm going to try and share my slides. It's that part of the presentation where we hopefully see that it works. So hopefully you should see some slides now.
So we're seeing the regular
It should be. Yeah, you should.
slideshow, not the presentation mode.
There you go.
Okay.
That looks great.
There you go. I know a lot of interest will possibly be around the eVTOLs around this presentation. The picture there literally paints 1,000 words. Most of our research has been done on helicopters in the real world and simulations on eVTOLs. And the key part of the work we do lately is how do you relate current knowledge to future aircraft? So we've published a paper recently, CAP 3075, that's available on the CAA webpage. CAP 3075 is a fairly light read, I would say, but it's backed up by another paper that I'll reference during the presentation that Richard did a lot of work on, that has the maths and so on. I'm going to start by presenting the background and the philosophy to the work. And obviously, because of that interest in eVTOL that the community has, there is a kind of a linear model of innovation, which is you start off with a lot of uncertainty and risk, and you try to winnow it down over time. If you're an OEM, you might generate a large number of initial designs, and then you fly a prototype, and then you refine that prototype, and you end up with an operational aircraft. And if you're a regulator, you kind of look at these new concepts and you think, well, what do we need to do to change things, potentially change regulations to enable them to fly? And that's a very straightforward process, and it looks very neat on the screen. Reality and innovation is often messier, however. But there is one about aviation. It's not entirely new. There is a lot of experience and knowledge out there. Can we use that experience and knowledge from current operations to feed it back into new concepts, into all the work that has to be done to get from the design screen onto the flight line? And the key thing, I think, is that with innovation, it's all about change. There are things you hope are going to happen that don't, and vice versa. But if you focus on your objectives, which are safe, reliable aircraft that make money in space and give consumers what they want, then you can be flexible in the processes. And that's the approach we've taken in part of the CAA. So we have an innovation team who are doing the left hand of this picture with industry. We're also working with the right hand of this picture from the operations perspective, trying to see how we can work with our innovation colleagues, inform them from current operations. And really the way I think of it is we're out to kind of flatten the speed bumps that may be lying in the way of innovators so that they don't have any surprises. But one surprise we did have was an accident in the UK 3 years ago now, where a search and rescue helicopter, a Sikorsky S-92, was landing at Derriford Hospital. In the UK, because we don't have many wide open spaces, hospital landing pads are often quite close to the hospital. In this case, it was in the hospital car park. There was what they call a blast wall to try to protect the public. But a member of the public was blown over and tragically killed. There was no fault from the operators and the pilots. It's just the nature of downwash and the proximity of the third party. Obviously, that gets a lot of attention in terms of any aviation authority. Uninvolved third parties on the ground are a no-no. You just don't want anything to happen to them. Certainly not a fatality. So what we wanted to do is, could we learn from this incident and consider possible risks for eVTOL downwash so that we can enable eVTOLs to operate safely and for people on the ground to remain safe when they do so? And the objective really is to kind of push down that learning curve earlier on in the cycle from current experience. So the process I've named it is Operation Innovation Research, but it is very much working backwards. It's working from the current world we're in and trying to inform future innovation as it's coming down the pike. So with that theoretical aspect looked at, what we considered was, well, we kind of want to go on a journey, and we don't want to just be preaching theory to people. We want to come up with a bunch of tools that they can use. But to get those tools, we'd have to do some work. And where we started 3 years ago was there was a body of work that's been created by NASA, companies like BAE Systems in the UK, Cranfield, DSL. I've worked in some of these places, seen some of this work. And in the CAA, we had already been informally considering this around eVTOL and helicopter downwash. Then the Derriford accident led to a directive from the CAA board that we need to investigate this. So we went out to industry for some research tenders, and Sophrodyne was selected. As doing the process of selection, there was quite a wide variety of approaches you could take to this work. The interesting thing about Sophrodyne was they had a novel software approach and not a novel simulation approach that personally in the past I've been skeptical about some CFD around vertical takeoff aircraft because it can be quite chaotic underneath them. So CFD may work in kind of straight and level flight situations, but with vertical flight it's quite complex. But Sophrodyne offered the possibility to tackle some of those complexities. So one of the things we did at the CAA is we came up with our own literal PowerPoint engineered configurations, very simple egg planes that you could add or take away different propulsion concepts to them so that we could compare digitally a range of different concepts. That was informed by the previous literature we had. That was handed over to Sophrodyne. They ran their simulations, and Richard Brown will tell you just it's not as easy as I just made it. I think some of the simulations, just kind of one scenario, would take 6 weeks to run. So quite a lot of software was running this, a lot of processing power. Sophrodyne wrote a report CAP 2576A, which is about, I think, 85 pages, if I remember rightly, very mathematical. We topped and tailed it with an introduction and kind of some appendices, and issued that as CAP 2576 in October 2023. But the key thing there was we briefed it to industry. We had some involvement. There were some offers of real world data, although at the time we weren't able to get them. But from the simulations, what we could see is they pretty well matched with what we expected from the work that had been done and the configurations we generated. But we did want to have a more specific verification and validation process. So we came up with this project called RAFD, a research assessment of transitory helicopter downwash. And the reason we went for helicopters was in the UK at the time we had no flying eVTOLs, but also as part of the work for CAP 2576, we had looked at helicopters, both conventional disc loading helicopters and an imaginary helicopter with the disc loading of an eVTOL. So there was a family of aircraft where we could hopefully learn about one type and then read across to another. And that was the approach to do. And we want to verify that initial part of the family, which was a helicopter. So we went to Silverstone in the UK, where the Formula One Grand Prix runs each year, and it's the busiest heliport, I believe, in the world at that point. There's a helicopter movement, sometimes up to every 10 seconds. So lots of people, lots of famous people come in on the helicopters to see the race and then leave. So there are two kind of bursts of activity in the day where you can actually see really hectic helicopter activity, but also quite sustained downwash and outwash. In some cases, quite brutal downwash from some of the larger helicopters. We also partnered with Snowdonia Aerospace, who provided access to facilities in Wales in the UK, airfield access where we could get a large helicopter come in a controlled environment. And Bristow Helicopters came on board voluntarily and provided a Sikorsky S92, which was of interest to us because obviously it's the type of helicopter that was involved in the accident at Derriford. Also, because it was large, we knew that we would be able to get significant readings from it without necessarily putting us in too much danger in terms of having to stand too close to the helicopter. So the object there was verify and validate what had happened in the previous work with Sophrodyne. But Sophrodyne also were given some data that we'd measured and asked to simulate that, see if what you can run in the simulation matches what we found in the real world. While this project was going on, we also got data from the FAA, where luckily they had 3 types of eVTOLs they could access there, and they had actually measured some real world data, so that was thrown into the mix. As you'll see, if you access on the CAA website CAP 3075, all that's written up. But the objective is to have these tools, and these are what we're now working on. But there was also a surprise, which was a cognitive issue. When we were doing the real world measurements, what we found is we became cognitively impaired. I'll go into the detail in that a little bit more. And it struck us that that's something that hadn't been seen before, but obviously for third parties on the ground could potentially be quite significant. So we also fed that into the approach of generating tools, and we briefed industry and incorporated the FAA data as part of that activity. So that's the history of these, 3 years, 2 projects, quite a lot of activity, but that's the background to the learning we had. But ultimately, it's about a very simple thing, which is what goes on underneath a rotor. So that's the simplest rotor that Sophrodyne, I think, simulated, which was, a 2-bladed rotor with no air vehicle. And you can see the vortices coming off the tips, and you can already see that it's quite a disturbed, chaotic situation. And as Richard will talk about, we have this assumption that helicopter downwash is just a perfect circle almost. But in reality, what we found and what we felt was actually it's much more turbulent, much more chaotic, and also unexpected in many ways. I think if there's mental models that are created by training handbooks and textbooks and so on that make you think it's going to be a steady wind, but actually it's a series of powerful gusts that you feel in a constant outwash field, supposedly. And it's the nature of those gusts that appear to be quite unsafe and cause risks for people. So we wanted to verify those simulations in CAP 2576. We did the work in the CAA's flight operations using internal CAA funds. So we can share the data openly, and we're happy to, if people contact us, we can go into more depth on this if you've read the CAP. But there's one of the tests at Carnarvon in North Wales. Sikorsky S92. The interesting thing here is that helicopter is about the rotor hub is about 80 feet from us. So we're not that far away. The rotor diameter is quite large, and at that point we stood there, we could feel virtually no downwash, and that was the first sign. That was actually the planned test point, and we got there and thought, okay, there's not much to measure here, and with a big helicopter that close, there should be. So that was one of the first signs that actually it's not just a circle of air that comes out. Bristow's, I think, were very clear that actually they themselves have experienced and found that downwash is an issue that they can manipulate in some ways. So the search and rescue crews have to understand it. They got people looking out the back all the time when they're on a mission. If they're over water, they can see where the downwash pattern in the water, and sometimes they have to direct that away from people that they're trying to rescue and so on. So they actually had in-house quite a lot of knowledge and experience of downwash and how to work with it, not just necessarily, you can't avoid it, but how do you live with it? And there was some interesting learning from that. But from the actual tests themselves, as you can see, when we walked a little way around the perimeter of the area where we're doing that test, actually suddenly we got hit by quite a strong downwash. So we were the same distance, we were still about 80 feet away from the helicopter rotor hub, but actually there was strong downwash off the nose where there wasn't when we were about 30 degrees off the nose. And one of the things we found was that, as well as the expected physical effects, so we used a process called a Bedford rating, which is where you look at task saturation. So some pilots may be familiar with this. And what we found is that physically, there comes a point where all you can do is try to stand up. You can't actually do the task. But actually, that's not as bad in some ways as the cognitive effects. And the cognitive effects, the task we were looking to do was to read numbers off a screen and write them down. Not hard at all. The Bedford scale is 1 to 10. Level 1 to 3 kind of was the task. It's a pretty straightforward task. But as you can see, in some cases, colleagues kind of got up to a saturation level of 10 with some efforts that they were trying to make to write down things. It was striking that certain colleagues who had experience of helicopter outwash or airliner jet wash actually cope with things cognitively better than those who hadn't had that experience. There was also a learning process as well, where we did a series of tests. Actually, once you'd experienced it once, you could actually deal with it better. So I do think there's sort of an issue there of the mental model that you have affects the cognitive impact. But it's an interesting area of research. Allying that with the desire to provide safety on the ground, it does make you wonder if having signs and notices perhaps is the best thing. Possibly maybe having people briefed before they go into a downwash environment, outwash environment may help, simply because what we were finding, one of the cognitive impacts was you would look at a screen to read a number, you would turn to your colleague to tell them it, and you'd forget it in an instant. So if you're forgetting written information that quickly, can a sign that is at the location where the danger is be necessarily that useful? So that was one of the puzzles, and I think certainly the material that Richard Brown will show you actually, I think, offers potential solutions to that. So that was the test setup. The picture I said where we felt no outwash is the tip of the yellow arrow there. That's the initial test point we planned based on if it blew us over, we'd fall onto grass. When we walked around a little bit to sort of on a line between the wind direction and the rotor head cross there, a lot of downwash. So you can see the nature of my graphical design, which is not great on the right, but that is the test case that was handed over to Sophrodyne. What the situation was, they were not given any measurements. They weren't told what we measured in terms of outwash velocities. They were just told the environmental conditions that we took the tests in, and then if they could simulate that. And as you'll see, they did a lot better graphical presentation of the simulations than I did in the tasking of that. But the key thing was we got quite good, I think, measurements considering we were using really coarse tools. Initially, my belief was we could do quite sophisticated analysis on the data and produce kind of distribution of probabilities and so on using Weibull analysis. In reality, the physical experience of feeling downwash made me question some of that, because actually, what does the data show versus what does actually seeing the air tell you struck me as being more important. And again, Richard will show that in some of the videos that he's showing. But what we did see when we got to see the air was these are simplified egg type helicopters. We also, Sophrodyne also simulated much more detailed S92 models. But what we saw was a lot of the training manuals have instantaneous average velocities in effect. The picture on the right there, there's a donut, a circular pattern of airflow. That's what downwash is. If you draw a line around that, you can stay outside the danger area. And what we found with helicopters was actually it's much more turbulent. The red is the higher velocities, and that kind of accorded with the experience. It literally felt like being punched by the air when you stood in front of the helicopter. It's not being pushed over by a constant force, it's being buffeted backwards and forwards. And actually that makes you quite, can disturb your balance, and it can be really challenging to deal with. At the same time, if you expect it, it's less challenging, is what I found, and other colleagues seem to. But you can see there on that picture that in some cases there's virtually, I mean, this image I like because it accords to our test conditions, which is 30 degrees off the nose to the left. There was virtually nothing that we felt initially, but right on the nose, there were more powerful flows that we could feel. The animations that Richard showed will bring this to life in a much more interesting way than the static images. But I think that image does capture the fundamental findings of a lot of the research, was that helicopters have chaotic patterns of outwash, just as we had predicted in our earlier work, eVTOLs would. And it's an interesting finding that we have lived with these patterns of helicopter outwash for a long time. So perhaps we can really learn from them to inform eVTOL operations. So there's a picture of one of the S92 simulations. As you can see, it's more detailed, much more accurate model. There's the sort of family of aircraft models that we did. So we have helicopter models feeding into certain eVTOL models from the CAP 2576 work that we did. But what we felt was that the verification and validation that we'd undertaken had worked within the hoped for outcomes. It hadn't necessarily followed the path we'd expected, but with all research, I think you have to expect the unexpected and deal with it as it comes up. And the cognitive side of things certainly brought that up. But equally, the chance to visualize air rather than just simply gather data on it, I felt was important. We did use simple equipment, and this is an approach that could be a method that the user community more broadly could follow with limited training. So I think that one of the interesting things about this work is it does offer the potential for a simple approach to be used by people to start to get a feel for this issue. But the outputs, really, the tools that we come up with are, and as Richard will show, the videos. I think we can use the videos that we use as part of the simulations actually for training. The visualization of the airflow is hugely important. I think when Richard first showed me one of his videos, I told him I wanted to give him a hug because it would save lives. It was that powerful of feeling, because I could literally see in the simulation what you feel standing in the position where I was in, looking at the helicopter as the simulation showed it. And it just struck me as something that could be really useful, and something we all have digital screens in our pockets these days. If people getting on an aircraft have a 30-second video they can watch before they go out, their mental model could be updated, and therefore they could be naturally safer rather than perhaps by reading a sign. Also, we'd like to do more tests. Unfortunately, resource constraints and availability of aircraft constraints mean that that's limited in the UK. But as I said, there was a huge body of literature, NASA tests going back to the 1950s and so on. So I'm working on the moment a thing called Vert AI, an AI model that actually captures those previous tests, the data from those, and allows them to be interrogated in a way that allows designers and users to actually start to get quantify and feel what maybe the outwash pattern would be like for this configuration versus that configuration. And also, we're going to carry out a proper Bedford exercise because the cognitive issue was unexpected. It was post hoc analysis. We did the analysis after we felt it. What we'd like to do is a proper structured Bedford rating exercise, so we can get a feel for both the impact cognitively of outwash on people, but also the potential mitigation. So if we train some people, or if they previously have been trained, does their experience change? So that's an overview of CAP 3075. Like I said, it's available online. Happy to talk about it if anybody's interested, who wants to get in touch. My contact details are in the CAP. And without any further ado, I think if we jump straight into Richard, unless Mike Hirschberg or Rex want to leap in, I'll stop presenting and move on.
We'll go right to Richard.
All right, let me see if I can start this successfully. Okay, hopefully you can see the presentation.
Yes, perfect.
Excellent. So yes, the outwash problem. Mike mentioned many times this idea of being able to see the air. And for the most part, the air is actually invisible, except on certain very lucky occasions when certain natural phenomena, for example, here, very humid air, allows for condensation and perhaps a visualization of part of the flow. So this is a very nice video. You've probably seen it before of an S92 in hover, and we can see condensation revealing the pattern of the tip vortices. The problem is the part of the flow that we're actually most interested in having a look at in terms of outwash is completely invisible to us. We can imagine that the air is streaming out across the ground, and we can see some of its effects in the trees and bushes that surround this particular landing site. So how, in real terms, do we go about trying to understand the properties of this outwash? And this is where numerical techniques come into play. So what we do at Sophrodyne is we use a very specialized numerical technique called the vorticity transport model to visualize the flow of air down through the rotors and out across the ground. Now, the VTM is a well-established method. It's been in development for something like 30 years. It's been used extensively to model various particular aerodynamic issues surrounding rotorcraft. But outwash was perhaps one of the most challenging applications of the code that we've come across so far. Let me try and explain to you a little bit of the detail of how we would go about simulating a system like this. The first thing, of course, is when you set up a numerical simulation is you have to have some sort of faith in its predictions. And so what you tend to do is you start off by constructing your code and verifying that it actually works mathematically, but then you go through a process called validation. And what that involves is comparing the predictions of the code against those parts of the flow that you can actually visualize in some sense. So what I'm suggesting here is that in a very simple fashion, we might go about comparing the predictions of the VTM, in this case of the positions of the tip vortices, with the positions of the tip vortices that we see in real life. And we might be interested in measuring, for example, the spacing of the tip vortices, how fast they decay down below the system, and trying to confirm that the code is working properly against what we see in reality. And that tends to be a back and forward process. So when you measure things in the real world, sometimes those measurements are subject to inaccuracy, and the numerics can actually inform better measurement process. And in some cases, the real world yields information which you can incorporate into the numerics and improve the predictions. And I think in terms of the outwash situation, that's exactly what we're looking at here. This partnership between numerics and real world measurements is where we're going to really make progress. But now, again, as I said, we're not seeing the whole picture here. So the real value in numerical simulations is being able to dig in and show parts of the physics which you cannot see by any other means. And that's what I'm going to try to explain to you in the next few slides. Okay, so let's step back a bit. So I'm going to step back really far, and there's my helicopter now hovering at some altitude above a big flat ground plane. Okay, we don't see much more than we would see in real life. But now let me do something. Let me take my numerical results and try to visualize those. And what I'm going to do here is going to plot a contour on which the vorticity in the flow has a constant value. The vorticity is the swirliness of the flow, if you like. It's associated with the tip vortices and the various structures that evolve as those tip vortices themselves disperse out across the ground plane. Now, let me go a short distance into one of these simulations. So let's say something like 6 seconds or 25 rotor revolutions, if we're talking in real terms. And what you can see when you start to visualize these contours of vorticity is that the flow out away from the rotor has actually a tremendous amount of interest, if not, and structure even. Okay, so what can I see here? I can see structures busy evolving out across the ground plane. And in fact, if I dig away at these simulations, I could see some of the fundamental physics taking place in front of my eyes. So those very fine tip vortices that I showed well, you can see them over here at the top of the slide. What we need to realize is that that vortical structure is inherently unstable. And as those vortices propagate down towards the ground and spread out, that instability morphs those vortices into much larger, more coagulated structures, which then propagate out across the ground. And eventually those structures all change in configuration and eventually dissipate through becoming tangled up in each other. And if you have a look very, very closely, you can see some very interesting features. Let me change my pointer here so that you can see a little bit better. But you can see, for example, 2 vortices catching up here and about to roll around each other and turn into a bigger structure. Here you can see a bigger structure already formed. And over here, you can see something really, really interesting, which will become very important when you talk about eVTOL outwash, and that is the formation of a hairpin structure on the ground. You can see this kink busy forming into like a, what do we call it, like a promontory, which will eventually lift up off the ground, turn into a vortex bullet and shoot out across the ground, causing very high local velocities. Now that's 6 seconds into the simulation. That's nowhere near enough to be able to understand what's going on in the full simulation. We have to run these simulations for hundreds of rotor revolutions before the flow actually establishes itself properly on the ground. So if I do that and I advance the simulation here to about 250 rotor revolutions, you can see just how complex that outwash field actually becomes. So there is structure sitting inside here, but that structure is slowly morphing as the flow moves its way out across the ground. These bigger structures form, they interact with each other, they coagulate, they intertwine, they crenulate, and eventually they destroy each other through forming smaller and smaller and smaller structures. Almost like a descent from order into chaos. I wouldn't call it turbulence, but it's order into chaos, if you like. Now, it's these individual structures on the ground that are responsible, in fact, for the velocity distribution on the ground. So if I try to show that, you can see in this picture here that the structures in the flow, these vertical structures, are responsible for the particular pattern of flow that we see out across the ground plane. So there we have it. We've gone from the structure of the flow to visualizing the velocity near the ground. And as in Mike's representation, what I'll do throughout this presentation is the higher velocities will be in red and the lower velocities will be in blue. Okay, now, as Mike alluded to, one of the big problems within the community is that the traditional view of the outwash is as this idea of this steady, actually symmetric stream of air out down below the rotorcraft. So the flow comes down through the rotor, bends out when it hits the ground, and just continues outwards as a radius, normally a radially symmetric, uniform stream of air. There's some theoretical justification for that particular approach, but generally what we're forced into when we do that is to adopt a turbulence-like approach rather than this order into chaos, this idea of vortical structures which evolve. Essentially what we tend to do is we adopt an approach which is something like this. We say that there's a mean velocity profile on top of which we can impose certain perturbations. But the whole idea is in terms of this mean, the steady flow of air on top of which there might be a little bit of wiggliness that might influence things. Now, the problem with that particular approach is that it's not particularly accurate, for one thing. The second problem is that this simplistic view of the outwash pervades a lot of the safety information that the industry presently relies upon. So to pick on 2 particular examples, you'll see in this particular report, here's this idea of this inverted cone of outwash spreading out across the ground, if you like, and a few interesting effects, perhaps, of adding wind or movement across the ground. Now, believe you me that when you look at the simulations of these particular cases, the flow is a lot more interesting than you see in those particular examples there. If we have a look at this particular example, then this momentum-like idea of the outwash coming down and hitting the ground results in a model for how that velocity varies out across the ground. Something like this. And that has informed quite a lot of safety information that we use in the industry up to now. But the model doesn't actually represent physical reality particularly well. Okay. Now, the interesting thing is that if I do run the simulations for several hundred rotor revolutions and try to calculate the average velocities in the outwash, then you do see this radially symmetric pattern. So the flow is actually symmetric about the helicopter, assuming that I haven't put in a tail rotor or any interesting fuselage interaction effects. But the flow tends to be actually symmetric and radially outwards in all directions. But this is only true in the mean. And the mean, calculated over several hundred rotor revolutions, has very little reality or relevance to the case of somebody actually standing in that outwash and experiencing the outwash, where we know from our simulations and from Mike's measurements that the snapshot of the flow, an instantaneous picture of the outwash, shows that the velocity is much more inhomogeneous. There are these wave-like structures, if you like, these gusty-like effects, which propagate out across the ground and cause the flow experience at any particular point to be very unsteady and difficult to negotiate, as Mike experienced. Okay, so much for the still images. What I want to show you now is a few videos which try to illustrate this in a little bit more detail. So this video shows how the velocity on the ground below this helicopter actually evolves with time. It's the S-92 hovering at fairly low altitude above the ground, and you'll see how the flow is actually very, very unsteady and granular. By no means radially symmetric. It consists of these waves of vorticity, which result in this gusty outwards flow of air out across the ground as time proceeds. I'll let that run to completion, just so that you can get an idea of how unsteady the flow across the ground can actually be. You can see how variable the flow is from time to time as well. Sometimes the flow is fairly quiescent, then all of a sudden a very strong and powerful gust will reach you, depending on where you're standing within that outwash flow. Okay, so let me skip to the next slide. What I want to do is I want to make things a little bit more tangible. Now, Mike had this anemometer and he was standing in the flow at a particular point. Let's make things a little bit more concrete. He was standing around about there compared to the position of the aircraft. What would he have actually measured with his manometer? Well, here's a trace of the predicted velocities from our simulations of the flow at that particular point over here. And what I've plotted is the radial velocity outwards in knots, so 0 to 80 knots, versus time in seconds over an interval of about 80 seconds. So we're talking about 400, 500 rotor revolutions in that particular case here. And what you can see very clearly is how unsteady the velocity at any one of those particular points actually happens to be. Now, let me try to go back to our old appreciation of the outwash in terms of the average velocities and these perturbations that are stuck on top of them. Whoops, if I try to get this to work, not having much success. There we go. That's the average velocity in this particular case. Now, the question that I would ask you is just what relevance does that average velocity have to the experience of anybody standing in that outwash? You can see that the flow is hardly ever equal to the average velocity. For most of the time, it's considerably lower. And then on occasion, there are these individual spikes in which the velocity suddenly goes significantly above the average velocity. So we need to question this idea of average velocities and this average flow and what relevance that actually has to the real experience of people standing in the outwash. And I'll talk a little bit more about that in a second. The next thing, of course, is that quite often we try to appreciate the qualities of the outwash in terms of the maximum velocities that are measured within the system. And you can see that what we're ending up with here is perhaps a system in which, if we looked at the maximum velocities over any particular time period, we might be significantly misled by trying to characterize the outwash in terms of maxima. In fact, we've all seen the reports that have gone out in the literature. eVTOL aircraft have hurricane force winds underneath them. Well, in this particular case, we also get hurricane force winds, 65 or so knots. but only once in the course of the entire simulation and for a very, very tiny amount of time. So if we were to report the quality of this signal in terms of its maxima, we would be severely misleading those people who are trying to assess the risks posed by this particular outwash. Now, that's not to denigrate the importance of these black swan events. You can imagine if this was a real feature and it came and those sorts of velocities came towards you, they would likely cause a tremendous amount of damage. So this is a very open question in terms of our understanding of outwash is, are these black swan events real, first of all? Secondly, how common are they? And thirdly, because they're so transient, what real effects do they have in the real world? Is the effect so quick and over so quickly that in fact we needn't worry about them? Or are these issues which we really, really need to take to heart? Okay, now let me try to make this even more real. Let me do something. This is a three-dimensional view of the same flow. Here's digital Mike standing at the position he was standing with his anemometer. And I've given him a slightly more sophisticated measurement suite than the CAA budget extended to by allowing him to measure the velocity at a whole set of points above the ground, a whole set of distances above the ground. Now, let me try and run that simulation and have a look at how the velocity varies in time according to the scale that I've put on the diagram over here. This is the knots, naught up to a much higher velocity over there. Whoops. And let me run that. Okay, and watch that scale and watch how the velocity changes as time goes on. Now, hopefully you'll agree that the numerics, when cast in this particular form, yields very visceral and direct insights into just what's going on in the flow. We can see how the velocities vary with time. We can see how the velocities vary with altitude above the ground at any particular point. And we can also relate how those velocities are interconnected with the various features in the flow that might be driving those particular velocity distributions. Okay, hopefully you get the picture. Now, what happens if I change the system a little bit? Now, this is an important issue. I think some of us in the community believe that perhaps outwash is an inherent characteristic of a certain aircraft. So a certain aircraft will produce a certain amount of outwash under all conditions. And of course, that's not true. The operating conditions of the aircraft make a big difference. So let me increase the height of the aircraft above the ground. And what you'll notice is, in fact, that the outwash pattern changes quite considerably. So first of all, the downwash streams down, hits the ground, turns outwards, and starts marching off across the ground plane in terms of all these structures. But you'll notice something interesting happens with the aircraft at this particular height. In this simulation, I've included the tail rotor, and what the tail rotor tends to do in trimming the aircraft is sometimes to drive the tube of flow coming down from the rotor out towards the side. And when that happens, you can see a highly directed flow of outwash coming in the direction of that distortion of the wake tube. Now, what that means for the velocity as measured at the ground is something quite profound. You can see that the whole quantitative character of the outwash changes just because the flow structures are changing in response to the operating conditions of the helicopter. So here we have this very high frequency variation. Well, it's a variation over a couple of seconds in these pulses of velocity, or these gusts of velocity that are experienced by the observer on the ground. Here we can see that these gusts are much more long-lived. There's almost like a rush of air outwards, which is then replaced by a quiescent period, which is then replaced by another rush of air outwards. And this is because of this redirection of the jet of velocity coming down, jet of flow coming down from the rotors and spreading out over the ground. Okay, and my very last slide in terms of helicopters is this one over here, where I thought what I'd do is I'd put you directly in Mike's place and allow you to experience the outwash with the aircraft in a high hover as seen by Mike while standing on the ground. And this is this video kind of illustrates the point that Mike was trying to make, where the idea is that perhaps we can present people with this sort of information a priori before they get on an aircraft or before they step into an eVTOL so that they can actually appreciate just what sort of situation they're going to get themselves into before they get into the aircraft itself. So perhaps much better than some obscure sign at the edge of a vertiport saying, beware downwash. If somebody doesn't have a clue what outwash is, then perhaps we've got a bit of an issue there. And perhaps they can watch this like a pre-flight video or something like that before getting into the aircraft. But here we go. We're immersed in the outwash. You can see this gustiness, these gusts heading towards you, and we can gain some sort of appreciation of just what it might be like to stand in the outwash below a large transport helicopter like this. Okay, now let me try to give you a bit of an appreciation of where we're going with this work. As Mike alluded to, part of the justification of this work is to extrapolate to the case of eVTOLs and to try to understand how eVTOL outwash is generated and what makes it different to that generated by helicopters. And these slides you're probably all familiar with. There's been a fairly extensive program of experimental research done in the US to try to quantify the outwash from certain eVTOL aircraft. Now, our initial work on this subject was published in October 2023 as CAP 2576. And you can get that report from the CAA website, and Mike's talked about it in some detail before. But one of the really surprising issues that we found with the outwash from eVTOL aircraft is firstly that because of their higher disk loading, the outwash velocities tend to be somewhat higher than those generated by helicopters with the same weight. But even more importantly, the shape of the outwash out across the ground is very, very significantly determined by the actual configuration of the aircraft itself. So in this case, what I've shown is one of our simulations of a rather exotic jet type aircraft where the propulsors are these linear jets rather than rotors. And here I've colored the wakes from each of these jets in different colors, and you can see the various structures that evolve. And what turns out to be very, very important in these multi-rotor cases is, of course, the interaction between the flows from each of the propulsors, because it's there where you tend to find most of the maximum velocities, or at least the most unsteadiness in the flow itself. But if you're interested in this, then I'll promote CAA CAP 2576 to you as a good place to start to try and appreciate some of the underlying physics. Let me instead show you some results from some newer simulations, which we did in the wake of the latest work. Now, what I'm doing here is I'm taking a representative eVTOL aircraft. This is not a copy of it. It looks familiar, but it's not a direct copy of any particular aircraft. Really, what we're interested in here is the basic configuration. So we have an aircraft with 12 propulsors arranged in this fairly linear pattern out across the wing, 3 in front of each wing and three behind. And what we've tried to do is we've tried to simulate the outwash generated below this aircraft in this case, a fairly high hover. What we tend to find is that the mean flow looks fairly benign. But if we look at the instantaneous flow generated below that aircraft, we see a very, very different picture. The mean doesn't encapsulate the range of velocities that we experience in the outwash below these particular aircraft. Now, with the aircraft at this particular hovering condition, fairly high above the ground, we tend to find that this destabilization process that's inherent within the wakes that I mentioned right at the beginning when I started has run quite a significant distance towards turning the wakes into a fairly disordered jumble of vorticity by the time it hits the ground. And so we see the effects of that in terms of the velocity patterns out across the ground. You can see that the velocity here is fairly unstructured, and especially if I look some distance out from the rotorcraft, then the velocity consists of these little granular lumps of high intensity or high velocity air spreading out across the ground. If I changed operating conditions again, though, by bringing the aircraft a little bit lower towards the ground, then again, the characteristics of that flow change. The mean flow suggests that, or this picture of the mean flow suggests that something much more interesting is going on. And indeed, if I run the simulation, you'll see that the structure of the outwash across the ground has actually changed quite considerably in character. So instead of these little granular pockets of high velocity spreading out, we now get this what I call this flaring behavior, if you like, where we end up with these rivers of high velocity air jetting out across the ground to quite significant extent, to quite a significant distance away from the aircraft. If you want to watch these movies in slightly slower time, then go along to my website, and there's a direct link to the whole set of pages of movies which support the CAA study. Okay, now here's the interesting thing. Let's superimpose that unsteady flow over the kind of array that was used by the FAA in measuring, for example, the outwash of the Joby aircraft. You can read their paper, and you can determine from their paper where the sensors were actually laid out. Now, here are a couple of bugbears of mine, actually, when we want to proceed in terms of how we might proceed in future in encapsulating the outwash produced by these particular aircraft. The first thing is that if we don't use a dense enough sensor array, then we're not going to resolve the velocity field of these aircraft in sufficient detail to be able to catch those points at which the velocity is actually maximal. So you can see with this particular sensor layout in this particular arrangement, we're missing completely any sensors in these highly critical areas over here where we end up with these velocity flares. Similarly, elsewhere in the flow, you can pick up multiple of those particular issues. The other thing that we might ask ourselves in terms of characterizing the outwash from this aircraft is how relevant is the characteristic dimension? Generally, if you take a fairly simplistic approach, there are some folk within industry who see the characteristic dimension of the aircraft almost like a rotor diameter, and see the outwash then through that the boundary of that characteristic dimension almost as this radially symmetric flow that you'd expect to see underneath a conventional single rotor system. And these sorts of visualizations show very clearly that that's nowhere near the case. The flow out in the outwash is much more directed and much stronger than you would expect in the case of the helicopter-related outwash based on the characteristic dimension. The second thing that we might ask ourselves is, are the presently proposed sizes for the protected areas at a vertiport properly defined and adequate? So here I have the TLOF, here I have the FATO. Let's not get too confused about the safety area. Remember that the safety area in this definition is the amount of area required to protect the aircraft from its surroundings, not to protect the surroundings from the aircraft. So not to protect passengers from the surroundings. Sorry, not to protect passengers from the aircraft, for instance. But you can see here that there are significant velocity perturbations extending way out of the FATO, well across the boundaries of the safety area and out into the domain surrounding the rotorcraft. And finally, we might ask ourselves, given this configurational dependence of the outflow, is whether our whole idea of a design vehicle for vertiport sizing is actually meaningful or not. And these are some of the issues that we're trying to address with this kind of research, trying to make a way forward so that we can gain some sort of meaningful understanding of the physics and then translate that into sensible, good, actionable guidance for those folk who are brave enough to go out and set up these sensor arrays in the real world to actually quantify and qualify these aircraft in terms of their outwash characteristics. But in summary, this harks back to the core of the research findings, if you like, which is in terms of how people experience the outwash while standing inside it. And as Mike alluded to, there is a danger that the way that we currently encapsulate both the physiological and the psychological response of humans to the outwash is going to be misleading in terms of how we qualify the risk associated with the outwash from these particular aircraft. So the historical approach, summarizing to some extent, is to characterize the outwash as this radially symmetric, smooth, uniform flow that decreases with distance away from the aircraft in a fairly monotonic and uniform way. And we're all familiar with the Paxpan model, which relates the steady overturning moment in the flow to the danger posed by the outwash. But of course, that data is all captured in terms of burly, robust American Marines busy standing, waiting to board Chinooks and CH-53s. Now, of course, when we go into the eVTOL world, our target customer community is a little bit different to your burly US Marines. It's grandmothers, it's children, it's infirm people, it's people with physical disabilities who might want to use this urban air transport to get from A to B. And in terms of acknowledging the unsteady nature of the outwash and this transient effect, this buffeting, this idea that the velocity comes from all different directions and changes significantly as time goes on, I think that is one of the crucial areas that this study has actually illuminated, and one of the key issues that we need to address properly as scientists and incorporate into our understanding of how the outwash will influence the people that are going to use these machines in future. Okay, so I'll stop there, and I'll stop the presentation, and hopefully there's still a little bit of time for some discussion.
All right, Richard. Fantastic presentation, both you and Mike. Thank you very much. We did get a few questions in the chat. I'm going to go ahead and go through those real quick. Kyle Ferguson basically states a paper, Mira et al. 2024 from the FAA was published, and in it they stated computer performance issues affecting the simulation data. It seems that it is not an issue here. Is there something drastically different about the modeling used here and the modeling the FAA used?
Yes, is the simple answer. We've written extensively about this. If you go back to 2023, I wrote a paper which I presented at the European Rotorcraft Forum, where I discussed in quite some detail the types of numerical methods which you might bring to bear, given what the community has to hand, and how effective those would be in terms of modeling the outwash below an aircraft as complex as an eVTOL, especially one with, let's say, 12 rotors. Not all numerical methods are actually up to the job. As I mentioned right at the beginning, this is one of the most demanding applications of numerical methods in the rotorcraft field that could ever be thought of. And one needs to be really careful in terms of one's mathematical formulation of the equations and how one goes about solving that mathematical formulation, that you're obeying certain very fundamental physical principles and mathematical principles. And the methodology that we use has actually been constructed to preserve those particular characteristics of the system. And hence, we don't have much of a problem with resolving the flows out to the distances required. It's a matter for a whole fairly academic lecture on why other methodologies fail to do that. But if folk are interested, I can always prepare a seminar on that subject.
Second question is from Peter Schmidt. Peter says, it looks like there is a characteristic fundamental frequency to the variations that I bet is a function of blade passing frequency. Have you looked at that?
It can be a little bit misleading to try to find natural frequencies related to blade passage frequency. It's tempting though, but I think it's fundamentally misleading. What you're seeing is actually a frequency which is related to the induced flow through the rotor. And then coupled with this instability, there's like a transit time that the vortices experience once they've wrapped up into twice the original size they had by engulfing a set of tip vortices, or 4 times the set of tip vortices, 4 times the size they were by engulfing even more tip vortices. And if we have a look at those transit times, you'll see there's a convection speed and sort of the idea of structures being convected at a certain speed. But by the time the flows have reached the ground and have spread out, the tip vortex effects have largely disappeared.
And Mike, I want to make sure I get you in here too. If you have any comments, please jump in.
On that one, I would just say that my assumption was a similar thing, that basically it's not a disk. It was a series of rotor blades spinning off vortices, and that would account for sometimes the patterns you see. If there's a shower of rain, you see some of these patterns looking like waves coming at you. But when you stand in it, you realize it is nothing like the rhythm of a rotor going past you. In the simulations that Richard showed, in some cases, you see that the air is coming from behind you. It suddenly reverses. So it's hitting you from the front and then it hits you from behind. The experience of it doesn't make you feel like it's predictable in the way that, rotor frequency would hopefully give you some predictability.
Our next question comes from Damian Rogers. Have the simulations been run using different ground type / materials and compared, i.e. changes to downwash, outwash based on hovering over concrete versus asphalt versus grass versus water?
Shall I just jump in there before Richard? So
Sure.
the measurements have been done around tarmac and grass. And actually, it doesn't seem to make a huge difference to the simulations, which Richard will cover in a second. We do have some initial ideas for doing some work on subscale physical modeling of different surfaces, because I know someone who does that kind of stuff. So trying to see if that can be done.
That encapsulates the answer. There are some people who are very interested in ground condition and contouring the surface or changing the properties of the surface as a means of perhaps even ameliorating the effects of outwash.
No, totally understand. Next question, Kareem Hijazi. What is the magnitude of differences between these outputs versus the ones determined based on the Ferguson model used to model peak wind velocity radiuses in hover in-ground effect?
Mm-hmm. So the Ferguson model is really interesting. It comes at the whole outwash issue from a rather interesting perspective. It says, first of all, that this is a momentum-like flow. So it says it's a jet flow which comes down from the rotors, contracts a little bit, and then expands out across the ground once it turns the 90-degree bend. But its essential formulation is in terms of a momentum theory, which relies on this idea of forces and moment, forces essentially being applied to the wake as it extends out across the ground. What they then do is they apply a correlation approach with a certain amount of experimental data to push and pull that model into closer correlation with the measured data. Now, what we see is quite interesting is that if you do compare the average velocities with Ferguson, you can see where the Ferguson model comes from. But in detail, things are a little bit more interesting than Ferguson actually shows. And hopefully by the time of the European Rotorcraft Forum in September this year, I'll actually produce some of the information which I verified, and I'll do a comparison with Ferguson to show you just what the differences actually are.
And I see that Mike Hirschberg has put a link in the chat box for anyone that's interested. It's the UK Civil Aviation CAP document and this Sophrodyne modeling simulation. You can go there and find the information on the link. Our next question comes from Fabrizio Morlando. What does the different direction of rotor rotation might influence the shape of the outwash? So does the rotation of the rotor have a influence on the outwash shape?
I'll let Richard answer this because we talked about it on Friday.
So yes. I thank you, Fabrizio. I think you're probably referring to the case of multiple rotors in general, where perhaps you can have rotors rotating towards each other and looking at the outwash in that direction or that direction in simple terms. And yes, there is a very distinct directionality of the outwash as a result of whether you're sitting on the if you think of this as like a cake mixer, if you're sitting on the inward side of the cake mixer or the outward side of the cake mixer. And what you tend to see is that the velocities down through the cake mixer are higher than those up, contrary to the direction of the rotor's rotation.
All right, and I see Mike could put another link in for the FAA testing. If you want to download the information, go to the link posted in the chat that Mike has provided. Fabrizio asks another question. It would be interesting to study the case where the downwash interacts with an uneven surface instead of a flat surface.
Yeah, absolutely. I mean, I did a little survey at Battersea Heliport, just looking at little steps and walls that they've got and cables that are lying around and kind of equipment, ground support equipment that they have. And it would be nice to be able to do a survey of a real site. I'm not saying necessarily Battersea, with those things in place. When we were at Silverstone, we've had a lot of movements and there was quite a lot of stuff on the ground in front of us. And in the CAP, I briefly talk about the attempts to try and deal with that. But it would appear that they make some difference, but not as much as you might expect. But I think there could be, a 2 foot, 3 foot high wall or something like that could really be significant, I think. But yeah, the modeling so far has been idealized situations. The measuring has been as close to ideal as we could get, but the real world is much messier and we need to understand that better. But looking for something that's an approach that's quick and cheap and reliable and allows you to make predictions is kind of where we're trying to take this work, hence using simple test equipment, sophisticated modeling, and doing it quickly.
Our next question comes from Mr. George Williams. Based on experience with interacting with manufacturers, they are often reluctant to expend resources on measuring or reporting something that is not required by regulation. How do you think capturing the downwash outwash for a particular airframe should be captured in an aircraft flight manual or aircraft document set?
I'll go first because it mentions regulation. So
Mhm.
I would say I'm not going to say anything about should, but could or might, because both these caps were kind of aimed at discussion. They're not regulatory documents. But certainly, first noting that there isn't a kind of a generic extrapolation. So you can't say a helicopter of this weight has a circle of that size and a helicopter of that weight has a circle of that size is a first step. But I do think you can measure them using, as I talked about, we use quite simple, cheap equipment. You could characterize the flow relatively straightforwardly, I think, using that equipment, that type of equipment, um, and then have a discussion with your local certification authority about what that means. And certainly some of the documents at the moment are out there around eVTOL are proposing certain test scenarios. Some of those I think perhaps could be changed. One of the most striking things is the height at which you measure. If you just measure at fixed heights, you don't capture as much as if we just measured at 3 different heights, but actually that gives you a different picture. And as Richard showed in his modeling, going up to kind of 10, 11 heights, you see there's a different profile and the profile changes quickly. But I think the first step is no one has innovated air. The thing we're measuring here is the one thing that all of aviation has to deal with. So just understanding the physics of it is the first step, but there's still a discussion to be had about how we would put that into a flight manual or any regulatory situation. But it's something we have to have with the manufacturers, and we have to have it in the spirit of we're trying to understand this problem so we can get past it if possible. It's not something we're trying to say, right, you've got to stop here. And I do think sometimes people think that if a regulator is looking into something, it's because they're trying to build their own wall to stop you. In reality, we're trying to help you over one that might emerge.
Next question comes from Mr. Don Burkhoff. Did you analyze how much the weather and the wind conditions impacted the wind gust or rivers of air? Were they enhanced or were they dampened?
Mhm. So if you go back to the original CAP 2576, there's a little bit of information about the aircraft at forward speed above the ground or in the presence of wind. But again, it's a huge open area. There's a lot of work to be done in actually understanding just what's going on there.
Yeah, and we did take it into account in the measurements, and some of them we took background wind readings and so on, and in other situations we tried to locate ourselves so we were, directly in line with the wind, either in front or behind, to make the calculations perhaps a bit simpler. But yeah, as Richard said, a lot more work I think needs to be done on that. The messy real world stuff. Although we've measured in the real world, we've tried to idealize it as far as we can so that it matches with the modeling, but we need to capture that messiness much more.
Nope, I have you. So we got time for one more question. And there's some other questions in the chat. We'll make sure that we share that with you so that you can, put your thoughts down on paper and we can post those later. Darshan asked, can we quantify the relationship between the shift of downwash created in high hover with increase in height?
Yeah, it's an interesting question, and one which almost gets to the heart of the complexity of the physics. So we're talking about a helicopter wake or an eVTOL wake, which starts off in this nicely structured, coherent form, but undergoes this instability and decreases in coherence with distance below the aircraft. So we understand something about that instability process and how these wakes degenerate in terms of their structure as they move towards the ground. But again, there's a tremendous amount that we don't understand, and we need to get to grips with. So eventually, I mean, this is one of the goals of the research, right? It's to say, okay, we do all these simulations, but if you're designing an aircraft or you're trying to regulate them or you're trying to figure out whether your vertiport is big enough, you're not going to be able to run simulations of this complexity every single time. So can we use these simulations in an effective way to gain an appreciation and understanding more generally of the physics that we can encapsulate perhaps in terms of rules of thumb, in terms of simplistic models that are actually worthwhile and encapsulate what's actually going on the ground in a meaningful enough fashion to be used by practitioners on a day-to-day basis. So it's a good question because it leads into this whole philosophical basis for the work.
No, appreciate that. With that, I'm going to turn it over to Mike to close us out. Mike?
Great. Hey, thank you so much, Mike and Richard and Rex for moderating, and thank you so much to all of the attendees here for this webinar and the great discussion. The fact that we've gone over 10 minutes and we still have most of the people still online, we really appreciate the engagement. You can see why this is such an important issue. And the Vertical Flight Society, as I mentioned, is really looking at this as a safety issue and how can we use the technical and engineering experience and capabilities to refine our modeling and protect more lives, especially as more vertical flight aircraft become in closer contact with the public. Again, stay tuned for more. We have the workshop at our annual forum, and we'll have more information going out electronically to all the people that registered for this event. So good night in Europe, and have a great day for everyone else in North America.
Thank you, Mike. Thank you, Rex. Thank you, everybody.
Indeed. Thanks for coming.